What's up, die-hard American metal? Welcome back. Ever stop and think what really makes tool steel, well, tool steel? Today, we're cracking open the chemical blueprint, the genetic code that separates a basic chunk of metal from the high-performance alloys that literally build our world. Let's get to it.
So here's our roadmap. First, we're going to lay out the fundamental challenge, why plain old steel just doesn't cut it. Then, we dive into carbon, the absolute king of hardness. After that, we'll meet the specialists, the alloying elements that give steel its superpowers. And finally, we'll see how the whole team comes together to forge something truly awesome. All right, so let's start right there. What's the problem with simple carbon steel? I mean, it gets hard, it's strong, but for the serious, high-stress, high-heat jobs we demand from our tools, it has some major fundamental weaknesses we gotta overcome.
When you're talking tool steel, you're always in the middle of a four-way tug-of-war between these properties. You crank up the hardness to hold a razor edge, but oops, there goes your toughness, now it's brittle. You boost wear resistance for a long life, but that might mess with other things. And hot hardness, that's a whole other beast. The art of making great steel is really the art of mastering these trade-offs.
So where does the journey to high performance even begin? It all starts with one single element, carbon. Make no mistake, this is the most important ingredient. It's the non-negotiable backbone that turns soft, useless iron into hard, capable steel. So how does this magic work? Okay, imagine the iron atoms are a perfectly arranged room. When you heat the steel up, the room expands, and the little carbon atoms can wander in and dissolve into the structure. Then you quench it. You slam the doors shut by cooling it down incredibly fast. The carbon atoms get trapped inside, distorting everything and creating a ton of internal stress. That new, messed up, highly strained structure is called martensite, and all that stress, that's what we feel as hardness. But here's the trade-off. Just adding more and more carbon gives you more hardness, sure, but it also makes the steel brittle, almost like glass. Even worse, if it gets hot during use, that hardness just vanishes. So carbon gets us into the game, but it's not enough to win. To build a true champion, we have to call in some help. And that's where the alloys come in. I want you to think of these elements as a team of superheroes. Each one is a specialist with a very specific power, brought in to solve a problem that carbon either created or just can't fix on its own. And here's problem number one. That super fast, violent water quench needed for simple carbon steel. Yeah, that's fine for a basic knife, maybe. But what if you just spent a month machining a precision die that's worth thousands of dollars? That kind of thermal shock can crack it in half or warp it into a useless pretzel. So who do you call to solve that problem? You bring in the specialist for stability, Chromium. Chromium's #1 job is to increase what's called hardenability. That just means you don't need that violent shock anymore. You can cool the steel down much more gently, in oil or for some steels, just by letting them cool in the air. By ditching the shock, you get incredible dimensional stability. No more warping, no more cracking. It's an absolute game changer for making complex tools. Okay, great. So our tool is stable and hard, but what about wear? What happens when you're stamping out 10,000 parts or cutting through something abrasive that's just grinding away at your edge? We need to armor up against abrasion. For this job, we call in the carbide kings. That's Chromium again, who helps out, but the real star of the show here is Vanadium. These guys are the undisputed masters of wear resistance. You see, Vanadium's special talent is forming these tiny, incredibly hard particles inside the steel called carbides. I want you to picture microscopic diamonds embedded in concrete. That's what these are like. They are so hard, they just refuse to be worn down. But vanadium has a secret second power. It also forces the steel's grain structure to be very fine, and a finer grain means more toughness. So you get this incredible 2-for-1, insane wear resistance without making the tool hopelessly brittle. And there's no better way to see this trade-off in action than comparing A2 and D2. A2 is your balanced workhorse. It's got great toughness, good wear resistance. It's just a fantastic all-around choice. D2, on the other hand, is a hardcore specialist. It jacks the carbon and chromium way up to pack itself full of those hard carbides. The result? Mind-blowing wear resistance. But you give up a lot of toughness to get it. The chemistry is telling you exactly what the tool is for. All right, final challenge. We've got stability, we've got wear resistance, but what about a drill bit spinning at insane RPMs, glowing red from the friction? Any normal tool steel would soften up in a second and be totally useless. So how do you make a tool that keeps its edge even when it's literally red hot? To conquer extreme heat, you need to call in the heavy hitters, the masters of hot hardness, tungsten and molybdenum. These are the signature ingredients of high-speed steels.
And these guys introduce a totally wild idea called secondary hardening. See, with normal steel, you temper it to make it a little softer and tougher. With these high-speed steels, you temper them at a very high temperature, and they actually get harder. It's counterintuitive, but it's true. They reach peak hardness at around 1,000 degrees Fahrenheit. This means when that tool heats up and starts glowing red, it's not failing, it's actually reaching its strongest possible state. That is red hardness. Just look at these recipes. You can read the entire philosophy right in the numbers. See A2? There's that 5% chromium for air hardening. Then look at D2. They cranked the carbon and chromium way, way up for wear resistance. And then M2 high-speed steel, it's got the whole team on the field. Tungsten, moly, chromium, and a healthy dose of vanadium. They're all in there working together. So we've met our team of specialists. But the real secret, the true magic of tool steel, isn't what any single element can do. It's how they combine. It's all about synergy. And that's really the key to everything we've talked about. The performance you get when you combine these elements is far more powerful than anything they could achieve on their own. M2 steel is the ultimate case study. You have tungsten and moly handling the hot hardness. Chromium is there to make sure the tool hardens deeply and properly. Vanadium is pulling double duty, adding insane wear resistance while also keeping it tough. And of course, you've got carbon, providing that essential hard backbone for everyone else to build on. You take away any one of those players, and the whole system falls apart. That's synergy. So the biggest takeaway here is this. A tool steel's chemistry is its DNA. It dictates everything. Its hardness, its toughness, its heat treat procedure, even the way it's going to fail. It's all written in the recipe. And this quote just nails it. Designing steel is never about finding one perfect ingredient. It's a series of intentional, calculated compromises. You're constantly trading a little bit of this to get a little more of that, all to build the absolute perfect material for one specific job. So now you've seen the recipe book, you know what the ingredients do. The question is, if you were the metallurgist in charge, if you could design your own perfect steel for your ultimate project, what would you put in it? What's your secret formula? Drop your ultimate alloy recipe down in the comments. I really want to see what you all come up with. Thanks for tuning in.